Alright, so again, last class we talked about points of concurrencies with perpendicular bisectors and points of concurrencies with angle bisectors. Today we're going to take a look at medians and altitudes. So first, let's take a look at your vocab sheet. Who can explain to me what a median is? Go ahead, Jen.
So it's like between, like it separates two like sides of the equal.
Okay, good. So it separates the two sides of the triangle equally. Another way we could say that is if we have our midpoint, we go from the vertex to that midpoint. So go ahead and just draw that example on the top corner of your page just to remind yourself what a median is. Now, how many medians do I have in a triangle? 3. Awesome. Okay. Now take a look at your vocab, and who can explain to me what an altitude is? Okay, Lucy.
An altitude triangles the perpendicular segment from a vertex to the line containing the side opposite the vertex.
Great. So we go from a vertex, and I want to go to the opposite side in such a way that I hit it perpendicularly. So this is an altitude. I think these are the hardest to draw. Sometimes what I like to do is turn my paper so that I have the vertex of the triangle at the top, and then just take my pencil and kind of adjust it until it looks like it's hitting it at that 90-degree angle. All right, how many altitudes do I have in a triangle? 3. Okay. So just like our other special segments intersected at one particular point, we have that same thing to be true for both medians and altitudes. So our first one we're taking a look at is our medians, and we have a theorem called the concurrency of medians there. Alright, so this is the medians of a triangle. The medians of a triangle intersect at a point. And once again, I'm going to leave a set of parentheses so we can fill that vocab word there. So medians of a triangle intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. The midpoint of the opposite side. So the medians of a triangle intersect at a point. And whatever that point is called, it is 2/3 the distance from each vertex to the midpoint of the opposite side. So go ahead and take a look at your vocab sheet. The point of concurrency of the medians of a triangle is called what? Centroid. Good. So let's go ahead and fill that in. It's called the centroid. And it's called the centroid here. So what we're saying is the centroid is 2/3 of the distance from the vertex, or 2/3 the distance from the centroid to the vertex. That's 2/3 the distance of the whole median. So let's go ahead and take a look what that means. We'll just go ahead and stick with median FH. I can see that FH is the median because it's been cut in half there. It goes from the vertex to the midpoint. So FH is my entire median. What this theorem is telling me is that the centroid, where is my centroid in my picture? C. Let's go ahead and label that before I forget. So the theorem says that the centroid is 2/3 of the distance of that median. So what we have is FC is 2/3 of the distance of the entire median, which is FH. So if the entire median is 30, how much is FC? 20. So if FC is 2/3 of it, how much is left over for CH? Right, 10 or 1/3 of it. So I'm going to go and write that underneath. So FC from the centroid to the vertex, that's 2/3 of the whole C. Now there's another way that I could, well, we'll just do it like that. So this is true for each of my medians. I could set that up for DC, I can set that up for EC as well. So we have from the centroid to the vertex, that's 2/3 of the same. Alright, so a couple things about our centroid. It is always inside the triangle. Which if we stop and think about it, that makes sense because my centroid comes from my medians. My medians always connect the vertex to the midpoint. Well, your midpoint's never going to go outside of your triangle. It will always be inside. So my median is always contained inside my triangle. And thus the intersection is always inside. What other fancy point of concurrency is always inside? Okay.
I just had a question.
Yes.
So, if that was perpendicular, would that be a perpendicular bisector?
Yeah. If it was perpendicular, it would be perpendicular bisector. And there's a certain triangle that happens in. Can you think of what triangle it is? Equilateral triangle, actually. Or an isosceles triangle with the vertex. Teresa, do you have a question? Okay. So, what special point of concurrency is always inside the triangle, other than centroids? In centers, good. So, those are similar in that they're both always inside the triangle. Now, this next piece is just kind of an interesting tidbit of information. I think this is pretty cool. So, the centroid is also called the center of gravity of a triangle. So, center of gravity of a triangle. And what that is it's the point where the triangle would balance. Okay, so let's go and finish out. It's called the center of gravity of a triangle because it is the point where a triangular shape, triangular that's a pretty bad abbreviation. Where triangular shape will balance. I found this to be pretty cool. So what that's essentially saying is if I take a triangle, any triangle, and I'm going to say let's cut it out of cardboard because paper is a little flimsy, and we were to go through and do all the geometry to find the centroid, that would be the point that you could bounce it on your finger and it shouldn't fall off. So, guys, if you want to impress the ladies out there, get those tortilla chips, find the centroid, and you'll have that point at which you can bounce that tortilla chip. So that's just kind of an interesting bit of information that relates to the real world. There's not a whole lot of math we do with that, but it's interesting to know. Okay, so our centroid, again, is 2/3 of the distance away from that vertex. That's the special property there. So let's take a look at this example problem. They say that SP is 6 inches. And then they ask for HS and HP. Which one is going to be the 2/3 chunk? HP or PH. Good. So I have that HP is 2/3 of the whole thing, PS. So how much is that actually going to be? The whole thing's 6 inches. 4. Good. 4 inches. Now, some of you just did the math mentally, so you could think to yourself, well, 6 inches cut in thirds would be 2 inches for each third. And so if I have 2 of those thirds, it's 4 inches. Or you could actually do the math and say HP, we don't know, that's what we're looking for, is 2/3 of PS, which is 6 inches, or 6/1. And that will give me 12 over 3, which is 4. Alright, so then how much is HS going to be? 2 inches. And again, you could just subtract what's left or multiply by 1/3.
So how did you know that HP would be the 2/3?
Good question. H is my centroid. The 2/3 is from your centroid to your vertex. Always to your vertex will be your 2/3 piece. Was there another question? I was listening. Perfect. Okay. Now, UR is 4 inches. This one's not quite as easy. I want you guys to go and try that one. If UR is 4 inches, find HR and HQ. All right, go and compare your answer with your shoulder partner real quick.
80 thirds and 1 third.
All right, I'm hearing some good answers. We should have gotten 8 thirds inches. And what was my HU? 4 thirds inches. So again, when the numbers start to get a little tricky, it's not easy to think of what's a third and 2/3 of 4. If I chop 4 into 3 pieces, just go back to setting up an equation like we did with algebra. So HR, that is going from the centroid to the vertex. So that's going to be 2/3 of the whole thing of UR, and UR is 4. Same thing as 4 over 1. Multiply straight across. That's how we get our 8 thirds. And then you can do the same thing for EHU. HU is 1/3, and then that left over amount, which is 4. All right, questions on that?
Should we use 2/3 from the centroid to the vertex?
Yes, yep. So centroid to the vertex is always going to be your 2/3 chunk. Good. Great.
How can you do it like HR was 2/3 and HU was 1/3?
So if I look at HR, that's the chunk that's going from your centroid to your vertex. That's always going to be the 2/3 piece. So going to your vertex is always a 2/3. Whereas HU was going to the side, that's the leftover piece. So now, what if they gave you some different information? So let's just come up with another problem. So we've got TQ is my last piece, right? Drew, give me a number between 1 and 10.
6.
6, sounds good. Oh no, that one's too easy. Pick an odd number.
7.
Okay, 7. Sorry, I like 6, but it was going to be too easy.
We already did 7.
I know, exactly. We don't want to do too much of the same stuff. All right, so let's say they give us if TH equals 7. Then I want you to find what is TQ going to be and what is HQ going to be. Changing it up here. So now you're not given the entire length, you're just given a piece of it. So again, we have a couple of options. I like to take it from the algebraic perspective. I know that TH, is this the 2/3 piece or the 1/3 piece? Good. It's the 2/3 piece of the entire thing, TQ. All right. Well, let's fill in what we do know. I do know that TH is 7. Got 2/3, and I don't know TQ. How do I solve for TQ?
Multiply by 3.
Multiply by 3/2. Same thing as dividing by 2/3, right? It's currently multiplying, so we divide by 2/3, which is the same thing as just multiplying by 3/2 on both sides. Alright, so I get that TQ is going to be what?
27 over 2.
Oh no, 21 over 2. Good. So I've got TQ is 21 over 2. Alright, so HQ, you've got a couple of options here. HQ is 1/3 of the whole thing, right? Or what else could I do? Amani?
You subtract 7.
Yeah, you could subtract 7 from 21 over 2. There's also another way we can do it, Teresa.
You could half the 7.
Yeah, we could half the 7. If we think about it, TH is 2/3 of the whole thing, right? And HQ is just 1/3 of it? Isn't 1/3 just having the 2/3? So we could, a little more quickly, get 7/2 of 3. But again, you've got your other options as well. Questions with that one? Alright, so now let's take a look at concurrency of altitudes there. So before we go to altitudes, I just want to recap. Our medians meet at the centroid, and our centroid is 2/3 of the distance from the vertex. Okay, altitudes. Our altitudes were the line that is from the vertex to the opposite side, and it's perpendicular. So our concurrency of altitudes here. The altitudes of a triangle intersect at a point. That's all it is. So our perpendicular bisectors, angle bisectors, and medians, all of their concurrency theorem said they meet at a point, and this point is da-da-da-da. For perpendicular bisectors, the point was the circumcenter, and it was equidistant from what? Vertices. And for angle bisectors, what did it meet at? In center, and it was equidistant from the sides. And for medians, that met at what? Centroid, and it's 2/3 from the vertex. Now our altitudes just simply meet at a point. There's no fancy property that goes with it. So take a look at your vocab sheet. What is the name of that point? Orthocenter is my favorite. It sounds so weird. So go fill it in parentheses and with flow. Alright, so orthocenter. Makes me think of the orthodontist. Orthocenter. So this theorem just simply says, hey, guess what? Your altitudes meet together, and it's called the orthocenter. But there's no special property with my orthocenter. Now, what's interesting with my orthocenter is that it can be inside, outside, or on the triangle. What other point of concurrency is similar in that way? Circumcenter. The circumcenter also could be all around. So I went ahead and grabbed this picture for you guys that nicely draws out what an acute triangle, right triangle, and obtuse triangle situation looks like with our orthocenter. So here in my acute triangle, the orthocenter is always inside the triangle. With my right triangle, the orthocenter is always on the triangle. And if you notice here, so my right triangle is this guy here. Well, again, the altitude goes from the vertex and is perpendicular to the opposite side. So if I go from a vertex to the opposite side, it's going to be the side itself because it is perpendicular. That's part of the right triangle. Likewise, with this vertex over here, when I go to the opposite side, it's going to be perpendicular because it's a right triangle. Then the last the last altitude goes from this vertex to the other side. So they all meet right here. Notice where they meet. They meet on that corner of the right angle.
Is it always that way?
Yeah. And it's because for a right triangle, the legs are always perpendicular. So those end up always being the altitude. Alright, so then for an obtuse triangle, we have that it is always outside the triangle. Alright, and so we see that for our obtuse triangle here. For this one, when I drew in my altitude, so here's my opposite side. This is so obtuse triangles are the weird ones where we have to extend out the side to help us to draw in our altitude. And we see that ends up falling outside the triangle. And then I can extend it out to meet my other ones. Likewise, for this vertex, I have to extend out my side here. And then it meets there, extend it out. And then this vertex, there's my altitude, so extending it out. We see our orthocenter is outside. So it's similar to the circumcenter that can be inside out. Alright, questions with that?
Why do we need to know the orthocenter?
It's actually, so there are many more extensions of orthocenters for later years of geometry. In my modern geometry class in college, there's actually something called Euler's, I think it's Euler's circle, sorry, not Euler, Euler's circle or Euler's line, which says that I believe it's the ortho circumcenter, maybe the incenter, are all in a line, that they are linear. Yeah, I might be wrong which ones those are. So it has to do with higher things than what we'll be doing in high school geometry. For us in high school geometry, that's all that matters for us.
So we just need to know what it is.
You just need to know what it is, yeah. And then keep in mind where it can fall depending on it. Okay, other questions with orthos? Okay, so let's flip it over to where algebra comes back again. Coordinate geometry. Woohoo! Yay! Alright, so it says find the orthocenter of triangle ABC. Again, let's just go ahead and draw a rough sketch to get an idea of what's happening. Alright, so I have A is at 2, 0. B is at 2, 4. And C is at 6, 0. What do we notice about two sides of this triangle?
They're horizontal.
We got a horizontal and a vertical. So what type of triangle is this?
Right.
Oh, how nice! It is a right triangle. What do we know about the orthocenter of a right triangle? It's on it. So what is the orthocenter going to be here?
2, 0.
Yeah, it's just that point A, which is 2, 0. Oh, that was so nice. How kind. Questions with that one? Yes.
Is it only on the right angle side?
It's always going to be wherever that right angle is, the vertex of the right angle. And so this is true for all of the right triangles, orthocenter. Alright, so let's take a look at our other one. Hopefully we have to do a little bit more work than that. Alright, again, let's just do a rough sketch. So A is at the point 1, 1. B is at the point 3, 4. And C is at the point 6, 1. Alright, do we have any nice lines in this one? Good, AC. So we have one nice side here. It's a horizontal side. Okay, so we'll just keep that in mind. Now, that may or may not help us out, but that's okay. We'll see. So it says find the orthocenter. And orthocenter, again, comes from our altitudes. And our altitudes have to be perpendicular to the side. I guess I should say to the side. And what else do altitudes have to do? They touch what? What do they go through? The vertex. Good. You can go through the vertex. So this is going to be similar to what we did with our circumcenters, and that we need to find the equation of the line for the altitude. But let's think about what the equation of the line requires. Alright, equation of the line requires a point, and it requires the slope. Well, what point is my altitude going to go through? The vertex. So they give us the vertex. We already have the point. We don't have to find the point. Circumcenters, we had to find the midpoint, right? Alright, and then we need to find the slope. Well, if it's perpendicular to the side, how do I take that slope and convert it to the perpendicular slope? Good. So I just need to simply do the opposite reciprocal in order to find my perpendicular slope. So same process, a little bit less work though. Okay. Now again, you get to choose which vertexes you want to work with. Personally, I'm going to go ahead and choose vertex B, because since this is a horizontal side, I know that my altitude is going to be a vertical side, right? So my altitude here is going to be a vertical line. And is that x equals or y equals? Good, x equals. But what is going to be the x value? What is x equal? 3. How did you know that, Cameron?
Because the point is 3, 4, and it's a vertical line.
Good. It's a vertical line and it must go through 3, 4. So x has to be that value. So we pretty easily already got one of our equations of the altitude. Now we do have to do a little bit more work to find our other equation. Alright, let's just go ahead and use vertex A. I don't know, look something like that, assuming I'm drawing it nicely. So again, for vertex A, we already have the vertex, but I've got to find my slope. So I know my vertex is going to be the point 1, 1, but how in the world do I find my slope? Talk to your shoulder partner. How do I find my slope for this altitude here? Talk with your shoulder partner.
The reciprocal of these. Yeah, that's
Oh, yeah.
it's the reciprocal.
Alright. So opposite reciprocal of what slope?
BC.
Good, BC. It needs to be perpendicular to side BC. So we just need to do the opposite reciprocal slope of BC. Alright, let's find our slope of BC. Alright, so BC 1 minus 4 over 6 minus 3. 1 minus 4 is negative 3. 6 minus 3 is 3. Anyone, do we agree with that? Okay, so that was my slope of BC. What do I have to do before I use it? Opposite and reciprocal. So my perpendicular slope would be what?
1.
Good, positive. Alright, so let's combine this together into an equation of the line. So again, I'm using my vertex A and the slope 1. So y minus 1 equals 1 times x minus 1. Y minus 1 equals x minus 1. What does y equal? X. Yeah, when we add the one over, our constants cancel out. We end up getting just the equation y equals x.
So it's 3, 3.
So our point is 3, 3. Good. So we've got our equation x equals 3. The equation y equals x. So when I go to substitute this in, y is just 3. So x is 3, y is 3. And that's our work. Yes.
How do you substitute x in 3a?
So what x value did you want to be? So we know that this is going to be our x value that gave us this, but then we still had to find our equation. Once we had our equation, then substitute it. Otherwise, we don't have, from here, I don't have anything to substitute that in unless I first have my equation. Alright, other questions on this? Okay. So now we're going to just do a short construction where we construct the median of the triangle and construct an altitude. We're just going to do one median and one altitude. In future stingers, we're going to go through and actually do all 3 medians, see that centroid, and all 3 altitudes that orthocenter. But with our median, so each of these are actually constructions we did before, just not in the context of a triangle. If we think about it, the median connects a vertex to the midpoint, right? What other constructions have we done before that cuts through the midpoint? Perpendicular bisector. So really what we're going to do is just construct our perpendicular bisector of this side to identify my midpoint, and then once I have it, then just connect them. Now for our altitude, again, we want just that perpendicular line. What we've done before, we did it quite a while ago, so it'll be, we'll be reviewing it, but it's been a little while since we've done it. Technically what we're doing is we're finding the perpendicular line that goes through a point that's not on the line. So we have our line, a point not on the line. So before when we did this construction, we had something like that, and then we constructed the perpendicular through. We didn't have the size of the triangle. So we've done this before. It just didn't wasn't in the context of the triangle, but we'll go over it again together. So go ahead and grab compasses. All right.
Okay.
They're drawn it.
Alright, so let's go ahead and start off with our median. And again, all we're doing really is just that perpendicular bisector to find my midpoint. So we should be pros at that by now. I've made you do it a few times, and you had to do it yesterday in Stinger. And I will show you in case you forgot. And bear with me, the smartboard was a little wonky this morning. Okay. Now, again, we're just doing the one. So we're going to do it of this bottom side here. So you want to take your compass and set it to be more than half the distance. And okay, so once you set it more than half the distance, then you want to go ahead and make a little arc above and a little arc below on one end, and just do the same thing for the other end. Now again, I'm doing this bottom segment, so I'm doing the endpoints of this segment here. Try to get as exact as you can. It's not going to be perfect. Alright. So I can already see I need to go back and do that first one again. I squeaked by on that. So that gives me your two intersecting arcs. Now, typically what we do, because for a perpendicular bisector, we actually want that whole line, right? But here we're just interested in the midpoint. So you can draw that whole line, but it's not necessary. Once you line up with your ruler, you can just make a little marking to know where your midpoint is. So normally perpendicular bisector, we would do the whole line and mark it perpendicular. So we are only interested in the midpoint. So I'm just going to do a little mark so I know where my midpoint is. So I'm going to move this guy. Okay. And then all we have to do is connect the vertex with that midpoint that we just found. So we're going to use your straight edge for that. I'm going to use my line because it works a little bit better. And there is my median. So again, go ahead and mark in your diagram that these are congruent so that can indicate to you that this is your median.
Does the median split the vertex into two congruent?
Great question. So Lucy asked, does the median do this? The general answer is no. In certain triangles that will be the case, but in general we don't know for a fact that it does. Good question. Other questions with this median here? Okay. Yes.
Can you erase that?
For grading, so on tests, I don't want you to ever erase the actual intersections. You can again clean it up. Like it won't let me on here, but like you could clean up to where you have just the little intersections. But I literally go through each person's construction with my compass and check to make sure that they went through it accordingly. So I want to see what markings you did to get that point. We will. At some point in time, we will have constructions.
Wait, like on the unit test?
It could be on this unit test. It could come again in the future as we get closer to school. All right. Other questions before we move on to altitude? Okay. So altitude, again, it's been a while since we've done this kind, but the idea of what we're going to do is take this point and find the perpendicular that goes through that line. Now, our first step for this is to put our compass on that vertex, swing it around here, and set it at a distance that will intersect the side in 2 locations. Now you can notice right now I have my compass just barely swept in there, but if your compass was set out a little bit longer, notice it intersects on that side, but it swings wide over here. So if you have that happen, you are always welcome to extend out the side. And I think I'm going to go ahead and extend my side just to give me some more room to work with. So I'm going to go ahead and extend this out. And then I've got a little bit more room to work with. So you can adjust your compass, extend out the side, do both, do one or the other. But I want to get to the point where my compass sitting at that vertex can intersect in 2 spots. I'm going to make my compass a little bit smaller here. There we go. Okay. So that's going to be my first step. Go ahead and intersect it on those 2 locations on the side. Because again, I'm trying to go from this vertex to the opposite side. So I want to sit on the vertex and intersect the side in 2 spots. That's my first step. Alright, now I'm just going to keep my compass the same width. You're welcome to change it, but I'm just going to keep it the same so I don't have to mess with it. And from those new intersections, I'm going to go ahead, if my smartboard comes back to me, here we go. So from that intersection, I'm going to do little intersecting arcs. And again, same thing over here. Intersecting arcs. Alright, so again, I put my compass on each of those intersections and did intersecting arcs. Questions? Okay, so then our altitude is going to be connecting this vertex with this down here. Again, we, for our altitude, only need it to go to the opposite side. So you don't have to draw in that entire way to the intersection. You can go ahead and stop at that opposite side. You're welcome to draw in the whole thing if you want, but it's not necessary because my altitude is just going from the vertex to the opposite side. And once again, go ahead and mark that it is perfect. Questions with that? Okay. So let's go take a look at this chart here at the bottom. This is pretty much just kind of summarizing what we've done the last couple of days. Alright, so last class we learned about perpendicular bisectors and angle bisectors. Today was medians and altitudes. So let's just go and write in some information here. So our perpendicular bisectors meet at the circumcenter. And what is the special property about our circumcenter? Good, equidistant from the vertices. I'm going to write equidistant from vertices. Alright, and is my circumcenter always in or in, out, on?
In, out, no.
Good. So we have in, out, and on. Okay, so that was our perpendicular bisectors with the circumcenter. Then next we had angle bisectors. Meet at the in-center. And in-center is equidistant from what? Good. Equidistant from the sides. And how about my in-center? In, out, on, or always in? In. Okay. So then today we learned about our medians. They meet at the centroid. I I don't have a really fancy way of remembering this. I see med, sen, and think just medical center. I don't know, median centroid. I feel like it's just about the same. But so I've got my medians meet at the centroid or medical center. If you want to use that to remember. And my special property is that the centroid is 2/3 of the distance from the vertex. So 2/3 going to the vertex. So again, going from my centroid to the vertex, this is my 2/3 piece. Right, 2/3. And then, are my centroids in, out, on, or in?
In, out, on.
In, always in, always in.
Oh,
Because my midpoints are always stuck inside my medians. And then my altitudes meet at the orthocenter. No fancy property for this. I'm telling you guys, I was really losing steam of this one. I thought always optimistic. Or you can just think altitudes orthocenter. Alright, what's the characteristic of my orthocenter? In, out, on, or in?
in,
And
out.
Good, in, out. So this is a nice chart here because it gives a picture representing each of these and kind of summarizes what we've been watching. Alright. Questions on that? So your homework for tonight, we have worksheet 4 and then the back side of worksheet 3 if you did not already get this. And if you would go ahead and put away your compasses and rulers. Like maybe before.